So, let us give a brief introduction to what would be done in today's class. We will do Stirling's formula, and we will also do applications of the microcanonical distribution, particularly classical ideal gas, which is what we were doing earlier. And this simple problem such as particle restricted to move in 1D, it is like a particle confined in a 1D box, and we will also do collection of spins in a magnetic field. And very importantly, we will do canonical distribution, the derivation of these probability for our system to occupy a particular energy state, that formula will be derived. So, overall an intense class, especially the last one, which contains a lot of conceptual things which would you have to understand it, you have to imbibe it, and then you have to apply it. Okay. So, instead of doing the Stirling's formula, which we will do just in a while, let us finish this classical ideal gas, which is we have done a part of it. So, we have this classical ideal gas, and as I said that it is the simplest prototype system for any statistical mechanics problem. So, we have calculated the number of microstates, and we have been using this capital omega to denote the number of microstates. We have of course calculated the volume of a hypersphere in say 6n dimensional space, or rather a 3n dimensional space for the momentum, which is restricted between root over 2 m e to root over 2 m into E plus d, or that small energy interval is given, and we have calculated the number of microstates there. But coming down to a simpler problem, we can do it in 3 dimension, and which is easy to do. So, this is like a d cube r I and a d cube p I, and this is subject to this one is subject to that condition, which is what we have said. So, this is a p square or p I square and 2 m E plus d E, or you can call d E to be equal to delta, which is what same as delta. Okay. The understanding is that d E or delta is much smaller than E. So, the shell in which you are considering, or rather you are calculating the number of states or microstates, that is much smaller than the energy itself. And the coordinate space integral gives you a volume, and this one of course can be done as so this is like a 4 pi p square dp, and that gives you a 4/3 pi p cube, and we are doing an indefinite integral because it goes from 0 to p. So, we have not used sort of limit for this, and if you use this relation that p square equal to 2 m e, this number of microstates, they go as 4 pi v by 3, and then you have 2 m to the power 3 by 2, and energy to the power 3 by 2. So, as the energy grows, the number of microstates grow as e to the power 3 by 2, and from there we can calculate the entropy, which is nothing but k log omega. Omega is the number of microstates, you take a log of that and then multiply it by k, and this gives you k and a log of all these 4 pi v divided by 3 and 2 m to the power 3 by 2. So, this is a constant for a given mass of the particle or a volume, and then there is a 3 by 2. So, let me write down that 3 by 2 here and a log of E. Okay. So, it goes as log of E, and this is what the entropy of the system is. And we know what entropy is good at. The entropy is actually good at giving you the temperature, which is so we have a 1 over T. We can calculate the temperature, which is del S del E for a given V and N, and we can also calculate the P by T using a del S, del V and E by N. So, I leave this small calculations in order to, suppose you do this, let us call it as equation A and equation B. You get the temperature of the system by sort of taking the derivative with respect to E. So, log of E is 1 over E, and so that will give you the temperature, and if you calculate the pressure by taking this, I am so sorry, this is del S del V. So, if you take the derivative of entropy with respect to the volume, you would get this the equation of state, which is P V equal to NKT. Okay. And you see the volume is inside this log, and then it is easy to say what that is going to be. So, this is a simple problem, and we can sort of solve more such problems in order to get the pressure or rather the equation of state or some thermodynamic parameters such as temperature, etc., or we can calculate other energy quantities as well. Okay. Before we go on to the next problem, let me do what is called as Stirling's formula. And in statistical mechanics, you would need the Stirling's formula a number of times, and let us state the result. The result states that log of n factorial is n log n minus n, where n is large. So, what it means is that when you take the log of factorial of a large number, it can be approximated as, so this is not really equal to, but it is almost equal to n log n minus n. So, the factorial goes away and you get this gets replaced by a simple formula. Okay. So, how do we use this, or rather where do we use this, we will just see in a while, but let me try to derive it or rather show you how this comes about. And let me take the left hand side, and which is ln of n factorial, this is equal to log of then you open a square bracket and it is n into n minus 1 into n minus 2 all the way up to 2 into 1, that is n factorial. And you know that when you take a log of x y, it is equal to log x plus log y. Okay. And that is how this becomes equal to log of n plus log of n minus 1 and so on, and then it is a log 2 plus a log 1 and something can go to 0 like the last term, but it does not matter, we will just write it like that, and then we will write it as a sum k equal to 1 to n log of k. Okay. Now, usually one can actually trivially replaces it by an integral and do that integral analytically to get this formula. But let me sort of do a little better than that, in the sense that let me try to show that this indeed becomes an integral. So, let me plot this thing, it will look like this. Okay. So, this is log of x and versus x, and what we need to do is that when you try to calculate the sum or the integral of this, we break it up into several such trapezium, and or rather here if they are too small and close to each other, they can be considered as rectangle and so on. So, we just calculate the area under the curve by summing up the areas of each of the rectangles that we see there. Okay. And this is easy thing to do, and let us say this is delta x, and suppose there are m intervals. Okay. So, m number of intervals between these 1, because the lower value is 1 and the upper value is some n. So, let us take a particular value here, let us call this as log of x k, and each one of them is delta x. So, we will have to when we complete or rather when we try to compute this area under the curve, we will have to multiply the function with the width of each of these rectangles, or the y is given by log of x k for a kth point, and then you multiply it by this delta x. This is a standard procedure to calculate an integral. So, the area under the curve actually is this is, let us call it as A, this is equal to k equal to 1 to m, m is the number of intervals as I said, and it is a log of x k multiplied by delta x, as you can see. Okay. So, as m tends to infinity, that is the number of these divisions, these intervals, they tend to be very large, you can actually convert this sum into an integral with reliability, which means it becomes better and better approximation. All right. So, this becomes equal to 1 to n log of x dx. This is equal to limit, you can see limit to be written as LIM, which is same as what I write as LT. Okay. So, limit m tending to infinity, and then there is this sum k equal to 1 to m and then log of x k and into delta x. Okay. So, that is the equivalence between the sum and an integral, and this is sort of has to be calculated. And now, what we do is that we what is delta x? Delta x is total length of the interval, which is nothing but n minus 1, and divided by the number of intervals. And this is nothing but equal to n minus 1, because the length of the interval, the last term is n and the first term is 1. So, that is n minus 1 by m. Okay. And it is well understood that n and m both are very large numbers. All right. And so, what is x k? That is, what is the value of this variable at the kth point, and that is equal to the initial value of x plus a k delta x. Okay. And this is the initial value is nothing but 1. So, this becomes equal to 1 plus k delta x, which is nothing but 1 plus k into n minus 1 by m. Okay. That is coming from the top line that we have written. So, eventually the integral becomes 1 to n log of x dx is nothing but a limit m tending to infinity, and there is a sum over k from 1 to m, and log of 1 plus k n minus 1 by m multiplied by k into n minus 1 by m. That is your delta x. Okay. So, that is your delta x, and this is your that log of x. Okay. Because n and m both are very large, n minus 1 divided by m is approximately equal to 1, okay, because n and m are same. So, then we have this integral as 1 going from 1 to say for example 1 to n log of x dx is equal to sum over k equal to 1 to n and log of 1 plus k. Okay. Now, realize that log of 1 is 0 and this sum goes from 1 to n. So, we can simply write that this equal to k equal to 1 to n log of k, and so that sort of tells you that which we did not want to write this directly as integral of a log from 1 to n, but that can be rigorously proved that this sum is what we have at hand, because this is the sum that comes here in the Stirling's formula, and this which is nothing but equal to log of n factorial. So, this is equal to log of n factorial. So, that is nothing but equal to log x or natural log of x dx. Okay, sometimes I will just keep saying log, but it actually means natural log, and most of the time that in statistical mechanics we come across natural log rather than log, the log base 10, though this base e. So, this can be now evaluated easily by using what is called as the integration by parts, by taking this log as the first function and 1, because there is no other function. So, we take 1 as the second function, and if you do that, then this actually comes out as x log x minus x. So, that tells you that we have this formula that we have is log of n factorial is equal to n log n minus n. Okay. Let me write it. So, this is log n. You can put this from 1 to n and sort of see that. So, this integral is this, and this you just put it between the two limits and 1, and you will see that 1 gives you 0, because there is no log of 1 is 0. So, this is the formula that we use, and this is called as Stirling's formula, and it is used heavily, at least in the calculation of the microstates and even later. Okay. So, let me do another problem. Let me state the problem first. So, this Stirling's formula can be applied, and also you know how to calculate these number of microstates in a microcanonical ensemble. So, the example problem is that we have n localized non-interacting spin half particles in a magnetic field. H. Okay. So, this is the problem, and you have to calculate the number of microstates. And not only that, calculate entropy and if other things that are possible. So, let me write it down as other physical properties. Physical means let us talk about other thermodynamic properties. They may be measurable by physical. Most of the time we mean that they are measurable quantities. Some of them could be measurable, but some of them could give rise to other quantities that are measurable. Okay. All right. So, this is what we have to do, and in order to do that we write down the number of microstates. So, we have this energy of the system, or rather the Hamiltonian of the system. Now, let me write down the Hamiltonian with a h, which is curly h. So, this is Hamiltonian, and we also have a magnetic field. So, should not be confused with these two h's. So, one of them is curly h, and the magnetic field is this h, which is written in normal font. Okay. So, this is equal to minus mu 0 h and then this is sigma j j equal to 1 to n. Okay. So, there are n spins, capital N number of spins, spin half. So, we replace it by this or rather we denote it by this symbol sigma, which should actually stand for Pauli matrices, which can take values here. They can only take values plus 1 or minus 1, and so this can be in two distinct orientations, which are up and down. All right. So, and this mu 0 is the say the Bohr magneton or magnetic moment, and we have n such spins. So, that this total number is n. Now, what happens is that in order to calculate this number of microstates, you have to understand that out of n, there are n 1 number of particles which are in the up state and n 2 number of particles which are in the down state. Okay. And so, total n is equal to n 1 plus n 2, and even in this n 1 particles you have suppose you have a up down and so on. So, you have a net magnetic moment here to be say 1 unit, and then you can also have this, and this also have a magnetic moment equal to 1 unit. So, the total number of configurations that one can write with this at a fixed value of energy and number of particles, there is no temperature here. So, we have to just write E and n. This is equal to n factorial divided by n 1 factorial divided and into n 2 factorial. Okay. And we have to calculate this quantity, but just writing this in this form is not very helpful, for the reason that you have to bring in the energy, and because this is a function of energy, and this energy will give rise to temperature and other quantities that are there. And it is easy to calculate the energy, because the total energy is given by a minus mu 0 h n 1, which corresponds to the spins that are pointing up, but this will also have to be added to one that is pointing in the downward direction, and they have a mutual sign change in between, because the sigma j will take plus value here. So, sigma j will be plus 1, and for this sigma j equal to minus 1. Okay. And just see that you do not want to carry on two variables n 1 and n 2, because they are related by this total number, and then we can write this as minus mu 0 h n 1 plus a mu 0 h n minus n 1, and so this is the total energy. So, what we can do is that instead of this n variable, we can use the E variable, but simply writing the n 1 equal to half of n minus E over mu 0 h, and n 2 equal to half into n plus E over mu 0 h. Okay. So, these two will now replace the denominator of this number of microstates. Let us denote it by 1, equation number 1. And so, writing the number of microstates in terms of E and n, we get this as n factorial half of n minus E over mu naught h factorial and half of n plus E divided by mu 0 h factorial. Now, you see that it is exactly the kind of variables that you want, it is a function of E and N. Of course, it is a function of H, but then H is just an externally applied variable, or it is an external magnetic field that you are talking about. So, this form is useful because this form can be once you compute this thing in closed form, you can get the entropy by taking the log of this and multiplying it by the Boltzmann constant. Okay. So, log of omega is what is important, and when you want to take log of omega, you have to take a log of this n factorial minus log of these two terms, which are n minus e over mu 0 h and minus log of half n plus mu 0 e over mu 0 h. Okay. I think it is clear, because again log of a by b is log of a minus log of b. This is what has been used. So, the log of the numerator minus the log of the denominator is what is used. Now, we will use Stirling's approximation. To all the three terms, that is the first term on the right, second term and third term, all of these three terms will use that, and then we can write down with a little bit of algebra, this is equal to n log n minus n. Remember the formula, which is log of n factorial equal to n log n minus n, and that is what is written here. And then the second term would be half of n minus e by mu 0 h log of half of n minus mu e by mu 0 h, that is fine, e by mu 0 h, and plus half of n minus e by mu 0 h, and we also have this other term, the third term, which is n plus e by mu 0 h log of half n plus e by, there is a h that is missing, e divided by mu 0 h, and again a plus half of, there is a h that is consistently missing, but put it. Okay. So, this is the expansion using Stirling's approximation on each one of the terms. Now, you see that there is a term which is n, and then there is a term which is half n and half n there. So, this minus n will cancel with each of these half n's, and then we shall be left with n log n minus half of n minus e by mu 0 h log of half n minus e divided by mu 0 h, and there is another term which is minus half n plus e by mu 0 h log of n plus e by mu 0 h. Well, I mean there is no third bracket here. So, we are fine. So, that is your term that is there, and then of course, you have these term, that is this term cancels with this term. So, there is no other term that is present in the expression. So, it is a log of omega and it is a function of E and N, and you see only E and N on the right hand side. And now we can use that energy per particle just to scale out the capital N from the problem. So, this is it's equal to E over n, and let us call that as small u. So, you will see that per particle is always derived or rather denoted as with a small case, in this case it is small u. So, limit E going to E and n both going to infinity, that is very large. So, we have a 1 over n log of omega. Now, this is not a function of E anymore, but we will write it as u n. This is equal to a log 2, and there is a half of 1 minus u by mu 0 h, log of 1 minus u by mu 0 h, and there is a minus half 1 plus u by mu 0 h, log of half. So, there is a half factor that I missed here, half of sorry, this half factor is not there because we have taken this half. So, there is no half there here. Okay. So, this is fine. So, we will write it as log of that, and there is no half there. So, there is a half factor here. So, it is 1 plus u by mu 0 h. So, that is the expression for when we divide the number of microstates by the total number of particles. So, the entropy is given by, so this is equal to, we will call it entropy per particle. So, it is S over n, which is, let us call it as S, small s, which is a function of u, which is equal to k log 2 minus half k 1 minus u by mu 0 h, log of 1 minus u by mu 0 h, and there is also another term which is almost similar to the second term, which is 1 plus u by mu 0 h, log of 1 plus u by mu 0 h. So, that gives you the first thermodynamic quantity, that is an entropy. And as you know that entropy is an important quantity, because if you put it in second law of thermodynamics, it gives you information about or rather combine first and second law, it gives you information about the internal energy, it gives you information about work done and all that. So, importantly, here the temperature, which is nothing but equal to del S and del U, of course, n constant, I am writing it as n, and this is equal to k over 2 mu 0 h. So, take a derivative with respect to u. Keep in mind that you have a coefficient which depends on u, which is 1 minus u by mu 0 h or 1 plus u by mu 0 h, and then there is a log term. So, you have to do a sort of x log x derivative, which gives you a log x plus 1, because x by x will give you 1 and so on. So, that is how we take the derivative, and so it is a del S del u, so this is equal to log of 1 minus u by mu 0 h minus k by 2 mu 0 h log of 1 plus u by mu 0 h. Okay. So, this is the temperature or the inverse temperature. You can easily obtain the other, I mean you can invert the relationship in order to get u, which is equal to the total internal energy divided by n, and that will come out. A little bit of algebra is required in order to get this, but then you have to convert the if you have log of x equal to y, you can write x equal to e to the power y and so on. Okay. So, use that, and then you would get it as mu 0 h tan hyperbolic, that is your mu 0 h by kT. This is an important quantity. This gives you the internal energy per particle, which is which depends on the magnetic field in a slightly non-trivial manner. There is a linear term here, and then there is also another term which depends on this tan hyperbolic, and there. So one can actually calculate the magnetization of the system by just simply using this thing that u equal to minus m h for small h, which is fine, and then this gives you the m, which is the magnetic moment, is equal to mu 0 h tan hyperbolic, m is equal to mu 0 not h, is a tan hyperbolic mu 0 h by kT, and so this is the magnetization of the system, and this is an important quantity, or it is a measurable quantity. Energy is not a measurable quantity, but however, it is important thermodynamic quantity, but nevertheless magnetization is definitely a measurable quantity. And if you really plot this magnetization, then let me draw to, so it goes as a tan hyperbolic, which has a form which is like this. So this is plus mu 0 h, that is the maximum value, and this is minus mu 0 h. So what it means is that when the magnetic field is large enough, because that happens at large values of field, well, this is tan hyperbolic, so this is more gradual, like the one that is shown above. So when the magnetic field is large, all the spins are pointing in the direction of the field, which means that it will have the energy will be minus mu 0 h, or per particle. So it is capital N into mu 0 h, and in the other limit, when you reverse the magnetic field, then at that instant all the energy of the system is plus mu 0 h, and then of course slowly all the spins start pointing down, or rather the spins start aligning with in the direction of the field, and eventually coming to an equilibrium, or rather this lowest value. But if we suddenly change the direction of the field, then this is what will happen, the energy of the system will be plus mu 0 h, and this has important consequences, which is what we shall discuss in the form of what we call as the negative temperature. Okay. All right. So we have done a few interesting examples, classical ideal gas, then these spin systems, and let me do this one more example. So we use this particle confined in a 1D box of length L. We have done this problem, but we have not calculated the entropy. So, let me just show that in a moment, and so this is the 0 energy and this is the two values. So, the only so particle confined in a 1D box, it is a free particle. So, let me just also add that the free particle. So, the only energy of the system is equal to p square over 2 m, and this is a root over 2 m e in the phase space, and this is minus root over 2 m e. This problem has been introduced earlier, and we take a small slice here and calculate the number of microstates, and because a negative momentum is also possible, that is why we take another slice here and calculate the number of microstates, and let us call this these thicknesses as dp. They do not look the same, but they are same. So, here dp is equal to root over m by 2 e dE, which is coming from P equal to root over 2 m E. So, if you take a dP and write it in terms of dE, it will become this. So, the total number of microstates for this EL and within this dE is nothing but 2L into dP, and 2L is nothing but, so L into this dP is nothing but 2m by E, and so there is a 2 there, and then there is a 2 which has been adjusted here. So, this is equal to a dE, and so the entropy again can be calculated for this particle which is free. It is equal to a k log omega, and which is equal to a k log of L root over 2 m log e to the power minus half. So, this is equal to a minus half k log L into root over 2 m log of E. Again we see that the entropy actually scales as log of E. So, that is how these microcanonical ensemble, or the number of microstates that are determined. And not only you determine the microstates, because this knowing the number of microstates is of no practical use. What is of practical use is to get the thermodynamic quantities such as entropy, such as pressure or temperature and so on, and we showed a few examples how we can calculate these quantities. Okay. All right. So, let me go on to something that is very important and should be taken very seriously in order to understand the crux of the statistical mechanics, the classical statistical mechanics that we are doing now, and this is the derivation of these canonical ensemble, or derivation of the probability of that my system is occupying a particular energy state. So, let us say given by E alpha or something. And why do we do that? We have explained this, that microcanonical ensemble is too much of an idealization because you have fixed the number of particles. In any case, energy is not a measurable quantity. What is measurable is temperature. So, you allow the exchange of energy between the system and its surrounding, and let the system come to an equilibrium temperature T, and we can now describe the system by this temperature T. And this example has already been given. If you keep a cup of coffee in the room and wait for long enough, the coffee comes to an equilibrium temperature T with that of the room, and the room acts like a heat bath, and temperature of the coffee goes down, but the temperature of the room does not rise because of there was a coffee present in the system. So, the rest of the room is actually taken as a very large number of copies of this coffee cup. So, everything else, so as if this cup of coffee which you have in your hand or which is kept on the table is actually interacting energy with all the other cups of coffee and coming to an equilibrium temperature T. So, my rest of the room, which is called as a heat bath, actually comprises of very large number of copies of this coffee cup, and that is how we define an ensemble. And this ensemble of systems which is here, which completely comprises of a very large number of coffee cups, and your cup is your system, and you are interested in finding out that what is the probability that your system occupies one of the energy levels. And once again, to remind you that we have said thermodynamics gives you only the equilibrium quantities, but it does not tell you the internal structure of the system, so that we have gotten this equilibrium quantities, and statistical mechanics tries to answer that question. So, now we are worried about that how different particles are distributed in different energy levels. so as to give me these thermodynamic parameters such as S, V, T, P and so on and so forth. Okay. So, having said that, we are going from a NVE ensemble which is microcanonical to a NVT which is canonical. Okay. So, there is no fixed energy, but there is a fixed temperature, and this energy is of course a variable between the system and the surrounding. But if you draw a picture, which is what has been shown earlier, that you have a system like this, let us call this system as A, and this occupies an energy level E r. I have written earlier E alpha, but I have changed it to r because this alpha and beta, which would be reserved for some Lagrange's undetermined multiplier. So, let us call it as E r, and so this is my system, which is A, and the bath, which comprises of all these copies of the system, which occupies the rest, and this is E r prime and T. The temperature is T. The accessible energy levels are E r prime for this system outside, and this is A 0 is the total system, which is again isolated, or rather this is not interacting with anything else, and then your system is A. All right. So, total energy of the system is E r. So, this total energy is E r plus E r prime. This is equal to E 0, and E 0 is a constant. Okay. So, the total energy which corresponds to the energy of the system, which is A 0, the total energy, and that is constant. Now, it is interesting to see that this E r, which only occupies a very small fraction of the total energy E 0, and that is equal to E 0 minus E r prime, because the total energy is E 0, which is equal to E r plus E r prime. So, E r is written as E 0 minus E r prime. So, this is equal to 1 minus E r prime by E 0. Okay. And this is much smaller than 1, okay, because this number is very large, and because E r prime, that is all the copies put together, all the members of the ensembles put together, all the microstates put together, takes the the maximum of the energy E 0, or the the lion's share of E 0, and that is how this fraction is a small fraction. Okay. So, the thing is that the energy available to the system is a small fraction of the total energy that is available. So, having said this, we can say that the reservoir, which is the heat bath. So, I will use both the terminologies so that you, when you read a book, you see both of them and they mean the same thing. The reservoir or the heat bath can still be in very large number of microstates. Okay. Your system, our system, let me write it as our system is in a specified microstate. I mean, when I say specified microstate, let me put a quote around it, which means that the available number of microstates is very few. Okay, it's very small, because the energy that it occupies is a very small fraction, and we've seen that these the ability, or rather the this probability to occupy some of the microstates, they scale with as some functions of energy. is in a specified microstate, and you can call it 1 or it is of the order of 1. Okay. So, if that is true, then let me at least start with this thing, because there are these to build up the ensemble theory. Let me take the number of possible microstates that the everything else other than our system is in. Okay. So, we calculate this P r, which is proportional to. So, this is what the probability that our system is in an available energy level R is proportional to omega prime E r prime. Okay. You understand, this is actually proportional to omega into E r. Okay. So, this is our system, and this is taken to be equal to 1. And that is why this is proportional to the number of microstates that all the other members of the ensemble would occupy. So, this is the probability that my system, our system, is found in an energy level given as E r, which is proportional to omega prime E r prime, because this is equal to 1. So, I will write it once again, that this is omega prime E r prime, and this is nothing but this is equal to omega prime times E naught minus E r. Okay. And you agree with me that E r is much smaller than E 0. Now, you are trying to find a probability, and initially why did I write it as a product? Because these are independent quantities. So, when you have independent events, the compound probability is going to be a multiplication of these two events. One event is all the members of the ensemble are all the other members of the ensemble apart from our system, they are occupying certain energy levels E r prime, and this is multiplied by the probability that our system is occupying an energy level E r, and this a multiplication of the two because they are independent, and so we have left this one out and said that P r is proportional to omega prime. So, omega prime or the prime variable corresponds to the other members of the ensemble leaving our system, and unprimed variable refers to our system. So, P r is actually the unprimed variable which refers to our system. Okay. Now, using this condition that E r is much smaller than E 0, what we can do is the following, that we can do a Taylor expansion of this, and instead of doing a Taylor expansion of this omega prime, we will do a Taylor expansion of log of omega prime about this value which is E 0, and taking E r to be much smaller than E 0. Okay. So, that gives you a log of omega prime E r prime. This is equal to log of omega E 0. Now, this is a constant, this you really do not need to worry about, because E 0 is a constant, and this is the total system which is again isolated. And now, we have a del ln omega prime del E prime E r prime minus E 0 and plus higher order terms, which we are neglecting at this moment because of this condition that you have E r to be much smaller than E 0. So, the higher order terms are even smaller and they do not need to be taken into account. So, you drop. So, one is a constant, the first term is a constant, which is taking this the first term in the Taylor expansion. So, just to remind you of the Taylor expansion. So, if you have a x minus x 0, it is equal to f of x 0 plus df dx evaluated at x equal to x0, x minus x0 and plus order x minus x0 square and so on, and those terms are dropped, which is what we have done here as well. Okay. So, this is a constant and all these terms. Now, if you use S is equal to k log omega, and then we can also use this 1 over t is equal to del S del E. This is a definition which you should remember. So, it is 1 over t like this. So, that tells you that 1 over t can be written as k del log omega del E, and then of course, this is a function of n and v. That tells you that del log omega del E n v, this is equal to 1 over k t, and this quantity is called as beta. Okay. So, beta you will see beta all over in statistical mechanics. As long as we do, we have this should be remembered, that is the inverse of temperature, but there is also a k factor, the Boltzmann constant that appears there and so on. Now, of course, you understand that beta and beta prime are same. We have written down T and T both to be same, whereas we have written the energies to be E r and E r prime. So, that tells us that at equilibrium, beta equal to beta prime. Okay. So, that tells us that a log of omega prime E r prime, which is equal to just a constant and plus this thing which is nothing but is equal to beta. So, this is equal to a beta E r prime minus E 0. I hope you understood that why there is just a beta and not a beta prime, because they are same. Our system exchanges energy with the other members of the ensemble and come to an equilibrium temperature T. So, a T and T prime are same, which means that beta and beta prime are same. Okay. So, now you see we can also write this as a constant plus beta E r prime. So, this is it should be E 0, pardon me for this, this is a E 0 minus E r prime. This actually went over here as well. So, this is a E 0 minus E r prime, and we can take it as a minus beta E r, because this is nothing but E r. Okay. So, this is a constant minus beta E r. I am so sorry, this was correct, just a little going back and forth, I am so sorry. This is really beta E r minus E r prime minus E 0. So, this is really E r prime minus E 0, and this is nothing but a minus E r, and that is how this becomes equal to this log of omega prime E r prime equal to constant minus beta E r. And so, P of E r, which is proportional to e to the power or exponential minus beta E r, because this quantity log of omega prime E r prime is nothing but P r, which is proportional to P r, and we have calculated what is omega prime E r prime. So, this is the probability that our system is in one of the available energy states with this probability. Okay. And because the probability has to be normalized, we shall write down this as this So, the sum over this is equal to 1, and so this is equal to a normalized probability is given by beta E r divided by sum over r, where sum over r means over all the available energy states of the system. It is exponential, or we can write it exactly in the same fashion, is exponential minus beta E r, and this is what has been told earlier. Now, we have proved that this is the probability that our system, and when we say our system, we really mean that any system that is under consideration, that is whether it is a classical ideal gas, or it is a collection of spins in a magnetic field, or a particle moving in a one dimensional box, or for that matter anything, group of harmonic oscillators, anything. So, probability that our system is in one of the available energy states. E r. Okay. And what is it good at? Because once you get the probability, this probability is nothing but the weight. Okay. And this weight gives you, when you calculate average values of quantities or equilibrium values of quantities, then you have to weight that particular observable or that particular quantity by this probability or by this weight. Once again, just to tell you that you may have you may be doing different courses in a semester, and each of the courses have different weights. So, xi is the weight of a course that you are doing. Okay. And this is one of your regular courses, and it is well known that if you doing these core courses such as statistical mechanics, classical mechanics, quantum mechanics, these are usually courses with standard weights or higher weights, say they have weights say 4, 6 or 8. Whereas, if you are doing say for example, a lab course which has usually a lower credit or lower weight, and so it is more important, as you understand, that for you to get a good grade in a course with a very large weight, and it will not matter much, not that I am saying that you should not do well in a course which carries lesser weight, but your grades are more going to be decided by the one that is which has larger weight and all that. Okay. So, we are going to calculate average values of quantities and so on, and then this average values of quantities will give us this thermodynamic variables such as say for example, entropy, or we will be able to derive the equation of state and so on. We will do that, but however, let us stop here by saying that this is a very important formula that we have derived. It you can call it as a Boltzmann weight. This is what we have said, that Boltzmann weight, and we will see that this is really a distribution, because a probability is like a distribution. So, if you this is for a general rth level, or it is the energy state that is denoted by E r, where E r is any arbitrary energy state of the system. We will see that this distribution is actually not a very broad distribution. The distribution is in fact a very sharply peaked distribution. And why it is a sharply peaked distribution is that only a sharply peaked distribution, that is the one with a few states, energy states, have the maximum weight. And this is a very important thing, because if we have equal weights to all the states available, all the E r states, then that may not give us the an equilibrium sort of value for a given thermodynamic quantity. And we have said this earlier that in the phase space all the microstates are equally likely to occur, or they have equal a priori probability, but then there is also a phase space density that we came up with, which means that some of the phase spaces may have more weight than other parts of the phase space, and that is the one that are more important in giving us or in yielding us the thermodynamic, the equilibrium thermodynamic quantities such as entropy, volume, pressure, temperature, and so on. So, we will look at this distribution in more details and do some calculations and the examples for the canonical distribution, just as we have done it for the microcanonical case. We will stop here.